going to talk about our work here with graphene, but we're interested in the transport properties, like electronic transport. So I'll show you how we get our samples and how we prepare them to make the measurements, and I'll show some results and some perspectives. Okay. Why is graphene interesting for transport? Because it has a linear energy dispersion, like we can see here. So we can have new properties that we don't usually observe in two-dimensional systems that we have. So how do we make our graphene? We use the exfoliation method or Scotch tape method. So you start with a graphite piece that you can see here. It's very big. Then you stick it in an adhesive tape, and you fold it many times until you get a very thin piece of graphite. And then you stick your tape in a clean substrate, and then you just look under the microscope and you can find the pieces of graphene. Here I show an example. We have a big piece of graphene. We have monolayer, few layer, bilayer. Okay, so we have to contact the graphene so we can measure the electronic properties. So we start with a graphene flake on a substrate. Then we use electron beam lithography to make the electric contacts. Then we want to shape the graphene into some shape that is good to make the measurements. So we make an etch mask, and we etch it in a oxygen plasma, and then we have the device ready. This is an SEM image, like it has a broken contact, but it's kind of the shape of our devices. Okay, so this is one of our results. Usually they use, to make graphene on substrates, they use silicon oxide because it's easier to see graphene on this substrate over a silicon substrate. And this silicon is usually highly doped because then you have like the capacitive coupling of your device is always the same for any temperature and any ambient condition. So you would have a shape like this for your resistance versus gate voltage. But then we made a device on a different substrate where our silicon was lightly doped. So what we observed was that the capacitance of the device depends on the ambient conditions and on your gate voltage. So when we sweep the gate voltage up or down, we have different curves. As you can see, this blue curve, when we are sweeping the gate voltage up, it goes low and then suddenly increases. And when you go down, it has a shape more or less what you expect. And this red curve is the curve when you have the device under illumination. So under illumination, you can see the same curve for up and down sweeps of the gate voltage. So what we observed here is that for the same gate voltage, we could have different resistance for graphene when it's illuminated, for the device illuminated, or in the dark. So what we proposed an optical switch with this device, because if you have some gate voltage here, then you apply some light, you can go to this state here of high resistance, and if you apply zero gate voltage, then you go back to this state, and that's what's shown here. When this is another device, so that's why the gate voltages are different. So when we apply some gate voltage. We go to some intermediate state, and then we apply light, so we go to a high resistance state, and then we make the gate voltage to 0 volts, and then we have the low resistance state. So you can use it like as a switch. Our works in progress are to make graphene on different substrates, like to use another oxide like silicon nitrate on highly and lightly doped silicon, and to put graphene on silicon dioxide over lightly doped silicon, that we had that result that I just showed, and also to put graphene on gallium arsenide, where we can have, in gallium arsenide, you can have a two-dimensional electron gas, and then we plan to study the interaction between these two-dimensional electron gases that we have in gallium arsenide and the graphene. And we are also trying to make graphene nanoribbons using focused ion beam patterning. So here we have a graphene sheet, and it's covered with aluminum, and we use the focused ion beam to etch some parts of graphene, and then we have a thin nanoribbon. This is work in progress, so we don't have like any electrical measurements yet. We also want to create modulating potentials in graphene, so we are trying to make these potentials with contamination or creating contamination or defects in graphene with focused ion beam, and also we can grow these alumina membranes, and they have self-aligning pores. So we want to use them as etch masks or masks for evaporation of metals under graphene. So we can create these potentials to modulate the transport properties of graphene. And also we're trying to get graphene on TEM grids, so we can maybe make some modifications in graphene using the TEM, like Professor Ijima just showed, that we can make holes in graphene or something like that, and then put it back on a substrate and make a device and measure the electronic properties. And I think that's all.